Good morning, good afternoon, good evening. Welcome to the Friday HSM Fast Track Hangouts. This week we have a very special featured guest who's typically with us here in the background, but we have the CAM Product Manager, Whatmough, with us. Al, thanks for joining us as the featured guest today.
Happy to be here. I figure I interrupt so many people, I should probably take a turn in the hot seat.
Yeah, and we've got a really exciting topic this week. This was actually one of the requests from last week's Hangout. Craig had requested that we provide some feedback on how to deal with large data sets. So that's what Al's going to jump into today. So before we get into Al's presentation, I want to ask the audience quickly, have you been to Autodesk University? We keep bringing this up week after week. The reason I'm bringing it up now is we actually have the classes have all been submitted, and we're asking the community to now vote on which classes you'd like to see actually present at Autodesk University. And I know a lot of the attendees here on the Hangouts are actually potential presenters. Al, who do you see in here that's potentially presenting in these classes that have been submitted?
Well, I know Rob Lockwood's on. He submitted a class. So thanks for joining, Rob. I don't know if I have anything I can teach you, but thanks for joining. I know he submitted a class. Generally, Seth's on with us. I don't know if he's on today, but he's got a class. Yeah, Seth's on with us today. He's submitted a class. Lauren sometimes calls in from the Netherlands, and he submitted a class. A lot of the level 70s. I'm excited to see submitted classes for this year.
So I think this is the first time that we've had 0 people asking what is Autodesk University. So a very small group of the audience has attended previously, and last year seemed to be the first year that there was a big focus on integrated CAD/CAM and HSM, and of course we want to increase that momentum and be a bigger part of the whole Autodesk ecosystem. So we encourage all of our community to attend Autodesk University. It's coming up in November this year. So I'm going to hide that, and then before we send it over to Al, one other thing that we want to ask is what's most likely to drive growth in your shop? As we mentioned every week, this is important. We've got the development team, we've got Al, the product manager, we've got the application engineers all present here. We want to understand what you're looking for, in development, future development of the product, also future, fast track potential topics. Where do you see future growth in your company coming from? And again, if you have specific topics that you'd like to see presented on these fast track hangouts, this week Al is presenting on large data sets, and that was a request, from last week. So please feel free to, in the questions box, please provide any, suggestions you might have for future topics. So I'm going to close this and share with the audience. And seems like a pretty, similar spread to what we've seen in the past couple weeks. So no surprising results here. So, again, in the comments, please let us know if there's other topics that you would like to see. And with that, I know, Al, a lot of people are excited to see what you have to present today. So I'm going to hand it over to you so you can go ahead and get started.
Okay, should be hearing me. Go ahead and get this presentation going.
While you're pulling that up, I did mention I didn't show the slide, but go to au.autodesk.com and you can vote for the courses that you would like to see at Autodesk University. Keep in mind, if you're unable to attend, you're too busy making chips fly, a lot of these recordings will be posted after the fact on au.autodesk.com, and you can see previous recordings on there as well. So please, everyone, go vote. We want to see HSM and Autodesk, the CAM, be a big portion of AU this year. So please, everyone, go vote.
Okay, is everybody seeing my screen okay?
Looks good.
Good. Okay. So I'm gonna try and bounce back and forth between Fusion. I'll present in Fusion. There's nothing that I'm presenting here that's Fusion specific. They're all concepts that apply equally to all of the HSM-based CAM products. The topic, again, Matt had said, it came up in conversation and sort of popped up here and there over many of the past webinars with different concepts around large data sets. Now, what do we mean by large data sets? It came up on Instagram quite a bit lately. A large data set could just as easily be a 5,000 end mill machining a penny as it is a 1-inch end mill machining a mold of a kayak. In a lot of cases, you end up with a lot of data if the size of the tool relative to the size of the part is a huge difference. So really the concepts that I wanted to talk about is things that slow your process down because you're starting to get to the limits of the software. Hopefully it doesn't come across as a bait and switch, but most of what I'll teach using some simple data sets so that we can quickly show the concepts. So the kind of three key areas where I want to talk about is understanding tolerance and smoothing. That plays a big part in both toolpath calculation and also how things run on the machine. Some things that we can speed up the simulation, so the stock removal, and then a bunch of different things relative to toolpath calculation. I've tried to flow this into a nice, clean presentation, but it just didn't seem to flow. So, like I said, I'll bounce back and forth a little bit. Those are kind of the key areas that I wanted to hit on. So let's start just taking a look at the multi-threaded side of the toolpath. At the same time, maybe we'll look at what the best tool for the job is. I often think adaptive clearing is sometimes overprescribed, so it's going to sound funny as a product manager to maybe not talk about one of the very strong toolpaths in our bag. But here we're looking at a mold of a kayak. If anybody's curious how a roto mold works, you actually machine a positive and then they fiberglass over top of that positive, and that creates the negative for the mold. So we're cutting this out of wood, and it's very likely that adaptive clearing isn't actually the best for this. So you might just use a 3D pocket. The main reason I wanted to show you this is if I just take a 3D pocket, I'm going to quickly grab a 1-inch end mill. Show you I'm still using the same 4th thou tolerance. I'm not doing anything fancy here. Maybe we'll put a 1/2-inch step down. We'll go ahead and calculate that. And if I can get my screen up fast enough, we can see that toolpath calculation not only calculated very fast, but we used all of the cores on the computer. So there's cases where if you're cutting a softer material, you want a very fast toolpath calculation. The pocket is a good example of a toolpath calculation that happens very, very fast and across all of the cores on your computer. Very similar parallel, so maybe we'll just quickly apply a parallel toolpath. In this case, I can use that 1/2-inch ball. Another thing to consider, calculation is going to happen a whole lot faster if your tolerance is a little lower. If it's a wood mold, maybe a 1 thou tolerance is good enough. So let's do a 1 thou tolerance with a 50 thou step over. Again, we'll calculate that, and I'm going to try and get my Task Manager up fast enough to again see that we're using all of the threads on the machine. Other toolpaths have different aspects of them that are fully multi-threaded, so some toolpaths aren't going to make as effective use of it. The other bit that I wanted to show, so the first thing is just kind of get you thinking about the fact that sometimes we overprescribe solutions, and when you're working with really large data sets, you might want to think about what strategies you use. So we've got a couple toolpaths here. Now it's just a few. It is a very large file, but there's definitely examples where calculations can be a lot longer. In this case, I'm going to use a distributed CAM. So if you're not using that, you can turn on the Task Manager. If you right-click Distributed CAM, we'll just check Distributed CAM, and you can see I've got my laptop running. It's a separate executable that you can download. Anybody can use it. Again, any one of our 3 CAM products will access it. You simply run it on another computer with the same local area network. When that's turned on, so I've now got my Task Manager open, I just right-clicked and said I want to show my server so I can see the name of the computer that's calculating the toolpath. And now when I go ahead and generate that toolpath or set of toolpaths, we're going to see one of them's happening on my laptop, and the other parallel operation is getting calculated locally on this computer. So if you haven't used Distributed CAM before, highly recommend that you give it a try. So those were kind of the first two things, just addressing some of the multi-threaded stuff, distributed CAM. If there's questions regarding it, we do have Renee on the line. He's the architect of speed. The reason a lot of our software is super, super fast. So if you want to dive deeper into that, Renee can be the one to interrupt me today, and feel free to ask questions. The next thing that I wanted to show is another very much Renee thing, but it's an exciting bit of the software. Sometimes people wonder why there's multiple nodes for simulation. So again, we're still looking at this large kayak mold. I'm going to hit simulate. Let's go ahead and hide the toolpath and show the stock. I'm in fast mode. When I click, I almost instantly get a preview of that stock. The fast mode is very, very fast. Maybe I should show a PowerPoint quickly to kind of understand why and how it's so fast. I'm going to quickly switch back to the PowerPoint and explain how fast mode works, and then we'll switch back. So the fast mode is what we call a needle model. So some of you may have used fast mode and say, well, it's no good. Why do you have it? Because it doesn't do undercuts. A needle model is like this thing you often see at the gift shop in an airport or something, where you can put it up against your face or your hand, and it very quickly gives you a representation of it. That's how the fast mode simulation works. And the different resolutions, we've got low, medium, high, extreme, is defining how many needles along the longest axis that you get. These things change as Renee optimizes things and the team optimizes things, but more or less you're seeing the number of needles that you get, and that's going to define the resolution. It's going to be important for what I'm about to show you now. So we have this full simulation. I've set it to extreme, but this model is 7 feet long. So the pixel density, the needle density really doesn't get me any sort of resolution that's any good to see a specific area. So I'm going to zoom in and let me know if my internet's lagging. I'm super excited they're bringing fiber internet to my neighborhood, but in the meantime, my current provider is kind of given up. So if there's lag,
yeah, this is Tim. It's a little bit choppy, but not too bad. I would say a second or so in between moving it around.
Okay, so I'll slow down here on my mess. So what I'm doing here is I'm looking into an area in my simulation that looks really choppy. And again, now that we understand how the needle model works, what I can do is I can right-click, I can say stock, and I can say zoom. And what that did is take the same number of needles, but put it under a smaller area. So maybe we'll do that again. I'll come in, I'll right-click, stock, and zoom. The experience is a little better in the desktop products. Just so you know, in the desktop products, you will get the ability to draw your box. But now we're seeing that I've got a much higher level of detail in the specific area. Why? Because I took the same number of pixels, if you will, that were spread across the entire kayak, and I've applied it just to this this area of the model. And again, we can click through very, very quickly. So I think it's important for people to understand. I think it's often missed, especially when working with large data sets. You just get to assuming that you should always use standard mode, but this fast mode is very fast, and hopefully now you have a better understanding of how that works. I'm going to take a quick peek at questions and see if there's anything that...
Looks like we're good with questions.
Good with questions. Okay. So the next thing I'll do, we can go ahead and close down this kayak and move on to the next one. This isn't going to be as much along the lines of toolpath calculation as this one is benefiting from a bunch of work that C.J. Abraham did at Pier 9 and speaks more to working with a large number of toolpaths. So I don't know how many people are utilizing this. CJ is very, very clean. I jokingly say he's one of the few guys that I know that actually puts medical gloves on to run a machine. I know a lot of people do it for pictures. I see CJ do it all the time. So he's clean both in how he runs the machine and how he sets up his files. So he's a good one to go get this from. But you can see he's making a lot of use of folders to organize the toolpaths, and he's got nested folders inside of here. So he's got folder with them organizing. These are the front pockets in machining, and then these are the next set of pockets in machining. So folders is a great way that we can just manage a sheer volume of toolpaths. While we're staying on that same topic, another thing you might do when you end up with a lot of toolpaths and you're bouncing back and forth is take a series of operations. If you don't want them to regenerate, you can right-click and you can protect those operations. So if you right-click and protect the operations, then they're not going to get regenerated. They're not going to get flagged as dirty. You're not going to have to worry about some of those other recalculation problems if you're down finally working on the hole down at the bottom and you want to almost break the associativity. It's not fully broken because you can unprotect and you can still recalculate later, but a great way to manage large amounts of toolpath. I know a lot of the files I see from Tim, he's in that habit because when he's finished something, he wants to know that that's done and kind of move on to the next step. Okay, the next.
I was going to jump in there. Yeah, I was going to jump in there. One of the good reasons to protect files is if you're ever kind of jumping back and forth with containment sketches or something like that, it's going to make them all dirty. So one good habit I have is to kind of protect them as I go along, and it's a mental check that it's done. But then I unprotect them and then kind of regenerate them right before I send it to the machine.
Sounds like a good way to do things. Okay, one of the other things on my list here was this this idea of patterns. I'm not sure if this was what you had in mind. I was poking around on Instagram the other day trying to see what kinds of things should be covered when you're talking about dealing with large models. I think it was Rob Lockwood that mentioned I should talk about patterns. Patterns are useful in a bunch of different ways. We have a component pattern many of you probably know about. A lot of Wayne's initial demos show how you can find other parts that are the same in pattern to it. In this case, I'm showing a component to fluidized bed. Many of you may or may not know the first shop I worked at was a university machine shop. We did models of buildings and bridges for wind studies and lab setups, and a lot of the lab setups for the chemical engineers, and they wanted to basically they blew air through particles and fluidized them, so it was a grid of a whole lot of holes. So anyway, we've got a whole lot of the same sort of reoccurring pattern. So in this case, I've used a pattern to create all those toolpaths. This is something that happens very, very fast because it's just a translation. There's no toolpath calculation happening whatsoever. I can say I want 15 instead of 10, and it calculates very fast because there's no toolpath calculation whatsoever. So sometimes we like to overuse the computer. I was thinking the analogy last night. I could use my GPS to drive to Home Depot in town. I know how to get there. It's probably going to take me longer because I'm going to sit in my car and set up the GPS to get me to Home Depot. I'm going to want to make some other decisions. Sometimes you're better off to just do the thinking and not always force the computer, and this is a good example of if you know of a pattern, you could speed your process up by simply using a pattern. A couple of things that are happening inside of the patterns. You can order by tool, so even though I had a roughing and then a finish and a chamfering operation, it's going to rough and finish each pocket because we're both using the same tool, and then move on to and do that for all of the pockets before doing the tool change. So it still will make use of that. The other bit that I thought was good timing, some people have asked for it for a while, and Bob Schultz finally did the FANUC post to support patterns. So I thought that'd be a fun thing to show. I'm going to go ahead and post process. You'll notice I'm using my cloud posts. If you're not using cloud posts, I suggest you do. Maybe I can show that quickly. So that's in my asset library here. I have my CAM cloud posts. I'm actually in a team hub, so you'll see this. I'm in a hub with the other internal Autodesk people on my team, so everybody in our team can see these posts that I've put here. But as an aside, so let's get back to me distracting myself.
I wanted to jump in and say that with the patterns, you could also multiple dices and do multiple work offsets that way too.
You can, yep, you can. So lots you can do with patterns. Sorry for the tangent on asset library, but definitely think you should be using that. Figure if I distract other people in their webinars, I should distract myself in my own. So I'm going to go ahead and use the FANUC post processor. This is the one we got off the post web page. If I scroll down, we're going to use this 3D arc thing later. That's a later conversation. You'll see some options. A lot of people miss looking at all these options. There's a lot the post processor can do, and a lot of people that are used to other CAM systems assume that a post processor sort of has a defined set of outputs. Because our post processors are almost an API, there's a lot of things that can get programmed into them, and then user-defined switches that can be set that can really fundamentally change how the post processor operates. In this case, Bob created some options for using subroutines for patterns. So if I go ahead and post, let's make sure wouldn't have worked if I didn't post my pattern. Let's make sure it's still set. The blue, incidentally, if you're watching for the first time, the blue just means we've made that option sticky. So I'm going to go ahead and post-process that out. And now what you'll see has happened is we are calling each of the operations. The initial tool call happens. We set the work offset with the G54. We turn on the coolant. We get the tool down to the correct height, and then it's going to call this subprogram for adaptive. Doesn't need a tool change, so for the contour, it's going to get us to the right location, set the tool length, and then call a subprogram. So instead of having, what is it, I think I had about 1,000 holes, pockets-wise, it's 60-some pockets. Instead of having 60 copies of all that adaptive clearing code, all of that's down at the bottom of the program in a subprogram that gets called each time. So the post processor actually reduced the amount of code you're sending to your machine because I've used the patterns. So hopefully that's a nice trick, more on the large data set sites for the machine. All right, I see Seth has got a question about tool libraries. I didn't come prepared to talk about tool libraries, Seth. I think that would be a great example. We should probably do a complete webinar on tool libraries. So if there's time at the end, we can talk about it a little bit. If not, let's do a webinar on tool libraries.
Also, quick comment on that. We have things in the works for organizing tool libraries regarding multiple setups and having multiple tool cribs. So stay tuned for that.
Yeah, thank you. And that's CJ. He's very close to the product development team on that. Is there another comment?
Yeah, would it make sense to show a duplication pattern on these holes? That way, Rob Lockwood brought it up as a more parametric way of doing a pattern.
Yeah, you could do a duplication pattern for the holes. One quick, Ben, on the post processor for the RoboDrill, right now it's only in that FANUC post processor. Bob is looking for people to test the logic and work through it. It currently only works in the XY plane too, so you're probably thinking you're wanting to do it on your little tombstone. That's not going to work right now, but if you're looking at testing the logic, there's a forum thread to search for to go take a look. The next thing I wanted to cover, and if we get back to the duplication patterns, I will. While we're on the theme of making code faster for the machine, let's kind of talk about tolerance and smoothing. Hopefully I'm not overly trivializing this. I tried to make some complex graphics and they got overly complicated. So then I kind of circled back to some simple graphics. On the left is, I'm using a circle, it's a very bad example, but you start with the model And then we're going to have a tolerance to create toolpath on it, and the toolpath is going to create a series of lines. And the number of lines you get and how close to that circle those lines are is going to be defined by the tolerance. If you have a very loose tolerance, then you'll get a very jagged stop sign. If you have a very tight tolerance, then you'll have a whole bunch of little lines, but obviously create more code. Conventional wisdom would have said, well, then I want to have a loose tolerance, and then I can apply smoothing, and smoothing is this idea of adding arcs, or it could be a series of straight lines over top of that to then reduce it, so my red line. The thing that I've seen a bunch of people confused with is this idea that it's actually better if you want to better fit an arc, you're better off to have a tight tolerance. So you have initial toolpath that's very close to your geometry, and that means your smoothing tolerance doesn't need to be as big because it can kind of lay over better across that. So hopefully this graphic describes that. And the next slide here is going to show some kind of research that Xander did. So first of all, we know that, okay, if I have a very tight tolerance and then a smoothing tolerance, I can get my code size very small, but the calculation is going to be a lot longer. So Xander was kind of playing with some of these toolpaths. There's a nice forum post on it. So the main thing I want to do on this webinar is give a shout out to the forums and to go scope out that discussion thread going on. But now you're starting to balance, okay, how can I split up my cut tolerance versus smoothing tolerance so a good toolpath calculation time in a small amount of code. Hopefully I'm making sense. I'm going to take a look at the questions here for a second. Keith, thank you. Keith's one of our experts up in Canada. He suggested I probably should have used an ellipse. You're absolutely right, Keith. It would have been described better with an ellipse, because a circle, obviously, I can easily fit a circle through it. So let's take a look at some of the impacts of that. I think it's going to make more sense on this kind of simple part, but again, maybe should have been an ellipse. So I've got this initial parallel toolpath. These first three toolpaths don't have any smoothing enabled at all. So we've created the toolpath. If I hit simulate, now I don't want to see the stock, actually I want to see my toolpath. And I've got show points turned on. I can see that I've got all of these tiny little line moves that, if this was a large model, would mean a lot of code. Is that hopefully that's making sense. So then what we do is I can go into the toolpath, and so this was the cut tolerance. How many little lines am I going to get to simplify things? Then we can say I want to apply smoothing, and that's going to go fit an arc through a series of those lines. So when I apply the smoothing to it, it does mean the toolpath calculation is a hair longer, but now you fit the arcs through it, and now I've got a series of large arcs that went through all the toolpath. And just to kind of visualize, here's an example of a toolpath that has a very jagged set of lines. Now the last, or the other thing that I thought was worth covering is I've often told people the trick that when you're using smoothing, you can look at the toolpath size, and that's going to give you a good idea of how things are going to run on your machine, but that's not completely accurate. So in the top case here, I've got my machining along Y where I didn't have smoothing enabled, and it's 33 KB. If I come down to the smoothing enabled, I've reduced my toolpath size to 5. So I've got a good idea that I made the toolpath a lot smaller with the smoothing. Now where is it that things get interesting? Well, things get interesting once you're not moving in the XY plane or flat on the Z plane, because not all machines support arcs going in every direction. Actually, very few do. So I'm going to take a look at the simulation on this. What we're looking at here now is our smoothing has found arcs that are at 45 degrees. They're not going through the XY plane at all. So it looks like I've reduced my toolpath size, but in fact, when I post-process this out, so let's say post-process, I'm using the FANUC post right now, and allow 3D arcs is turned off. I love HOS, but HOS is not an example of a company that supports 3D arcs, and like I said, most don't. Then we're going to hit post-process. I've got this NC code, and look at that. I ended up with a whole lot of line moves. Why? Because the post-processor understood the machine doesn't support an arc in any plane, and it's now linearized it into a whole lot of short line moves. This is an important thing to keep in mind because the post-processor does have a tolerance. It's actually set probably more aggressive than it should be by default. So you thought you got everything smoothed out by moving smoothing, and this could actually move you back in the wrong direction. So if I go ahead and turn on allow 3D arcs, I'll hit post now. Let's just call this 2. I now have a program where we've got this funny code you might not know, G 3.4, which is an arc that's in any plane. I'm going to give a shout out to Xander because he's been working super hard, so I'm going to do a Control A to select all and Control C to copy. We're going to go over to Xander's little NC backplot. He's got a ways to go. He knows the arcs aren't showing perfectly, but not every machine vendor supports 3D arcs yet, but the intern's working on it for his little backplotter. So if you're not using his backplotter yet, give it a try. We're talking back and forth this morning. He knows he's not fully supporting 3D arcs yet, but here's a representation where we're seeing a 3D arc. So hopefully that's helpful and a little trick for something to keep in mind when you're dealing with arcs in any plane. Okay. The next thing I wanted to talk about, rest machining is another area where toolpath calculations can quickly get out of hand. One of the main things is it forces things to be sequential. So if I want this pencil toolpath to be a rest machining of the parallel toolpath in front of it, when I go into rest machining, and by default I use from previous operations, now I've forced the toolpath calculation to be happen one after the other. So it sort of breaks the ability for distributed CAM to split things out and for some things to happen faster. So here's my toolpath for pencil with rest machining on, looking at the stock that was presented from the previous toolpath. There's a couple things to note. One, there's a little bit more noise in it, but 2, it couldn't calculate until this parallel was calculated. So maybe I should calculate both of those to show. I'm going to regenerate both those toolpaths. See how this rest machining toolpath was set to pending until the 3D toolpath finished. So the trick that I wanted to show here is I have now a pencil toolpath that A is very clean with no noise, and B does rest machining without needing the parallel to generate. How did I do that? Quick little trick. On rest machining, I used from tool, and I simply defined the diameter of the previous tool that was used, and now I get a very, very clean rest machining toolpath with far less noise, and it's not dependent on previous operations. So that's a great way that you can speed up some of your calculation. So it makes sense. I'm going to take another quick peek at the questions here. It doesn't look like there's too many questions. I covered a lot of what I was wanting. Okay, the next thing that I had on my list was clear toolpath. Maybe the kayak mold is a good example for this one. So if you have a toolpath that has large files, this parallel toolpath is 11 megabytes. Probably just for fun, I'll post this out afterwards to show the speed of the post processor. But I've got this 11 meg toolpath. I want to save this file, send it to somebody else, whether again that's with our desktop products or Fusion. I want them to understand everything about how I calculated the toolpath, but I don't want the file to be so large. there is an ability where we can right-click and clear the toolpath. So see this option, clear toolpath. That emptied the toolpath out, took that 11, 12 megabytes off of the Fusion file, off your SOLIDWORKS file, Inventor file, but everything about this toolpath and how we defined it is still there. So all that has to happen on the other end is a regenerate. So that's a way that you can reduce the file size if need be. Kind of an obscure little trick, but nonetheless, I thought one of those things that doesn't often get mentioned. Okay, see a question. I'm just going to read here. There's some tool library questions coming in that we're going to leave for a tool library specific conversation. Okay, so the next thing I wanted to cover, and this one comes up a lot, the adaptive toolpath is a very powerful toolpath. It maintains a constant engagement. The reason we call it adaptive clearing is it's constantly adapting the toolpath and adjusting it so that you maintain a constant engagement on the cutter. So the reason it's adaptive, you set an amount of engagement. It's kind of a seek and destroy algorithm. It finds stock. It adjusts the direction it's going in to maintain that amount of engagement. It's always adapting. It's always aware of what stock is there and what stock is left. So it can find these safe distances through the stock that's been removed. It even happens in 3-axis. I'm sure many of you have seen some of those 3-axis adaptive stay-down moves that weave through the part. It's very powerful, but it's also a very calculation-intensive toolpath. So I wanted to cover one quick thing that is often confusing and may very much help you think about how adaptive works. And that has to do with this stay-down level. So the stay-down, first of all, the stay-down is talking about these moves. Let's see if I can turn the pointer on. Here, little red pen. These moves down here where I keep the tool down instead of going up and over. Do I want to force the tool to stay down? How that calculation happens is the very fast thing for us to do is say, let's wrap it up, wrap it over, wrap it back down. That's the easy, fast calculation for us to do. So that calculation always happens regardless of what you've set for the stay down level. We take that value, so in this case it's 4.4 total traveled inches to do a rapid movement that goes up, over, and back down. I now know that it's 4.4 inches, and I set stay down level for this example, we said 50%. So now I'm starting to see if I can find a safe, faster way to get to where I'm getting by keeping the tool down. When it's set to 50%, this is probably weird to think about, but 50% means that the stay down distance would equal the rapid distance. So what happens? We know that it's 4.4 inches to wrap it up, over, and down. Now we start trying to find our safe path, and we're given 4.4 inches to work with. Well, actually, in this case, I'm given 2.5 inches to work with because it's whatever number's smaller. The maximum stay down distance or the percentage of the rapid distance. At 50%, they're equal. So I'm hunting. I didn't make it the whole way over, and I got to my 4.4 inches, so I give up and I stop. So that's effectively how this stay down level works. So understanding that means that the lower the percentage, the faster the calculation, because the algorithm can give up and stop looking for a solution once it's sort of met that threshold. So that's why that slider is in there, among other things, is it allows you to kind of control a balance of how much calculation you want versus how long the tool should stay down. The other thing to keep in mind is obviously you generally want a lower percentage because your rapid speeds, I mean, if you're Rob Lockwood with the machines he's working with, you've got several thousand inch a minute rapid speeds, and that's going to be a lot faster than maybe how fast you want the tool going when it's inside of the part. So generally speaking, you're going to want it to be a much lower percentage to really even be saving you any time. So let's take a quick look at this this example here. So I've got my stay down level set to least, so it's coming up and over all of the time. Here it's set to most, and it's staying down all of the time. So most is, we didn't say 100% because it stops being a percentage, and it just says, just doesn't matter how long it is. Go do it. Here we're set to 50%, and it's not going down. And just to demonstrate what I'm talking about, I'm going to edit this. I know this is 4.4 inches right now. I need this rapid to be more than 5.5 inches. So I have, 1.1 inches to add to it. So let's go to the heights and change my retract to 1 instead of 0.5. And we'll recalculate. It's still coming up and over because it hasn't reached that threshold yet. I'm going to edit this again. I'm going to change my retract height, so I'm just changing the length of these 1 inches on either side. If I change that to 1.1, now it's going to add up to 5.6 here. Oh, I better make this taller. So made that a hair taller, and now the percentage was met, and that meant it could look longer to find the stay down distance. Tim, as a third party, does that make sense to you? I know it's confusing, so hopefully that helps you understand.
It's it's kind of a deep conversation, but that does make sense to me. I think what you did with the graphics is pretty awesome. So
good. I even have a shout out from Rob Lockwood, so I'm excited.
How does it know that the rapid stay down is going to be 5.5 inches in this case without calculating that beforehand?
It doesn't. So that's the point. It calculates the rapid first. The rapid is one line up, one line over, and one line down. It knows how long that is, and the percentage tells it this is how hard you can look for a solution. So it's searching its way through the stock, trying to find its way home. And once it's walked 5 inches, it gives up. It doesn't know if it's going to take 12 inches because it says you're done calculating. Stop trying.
Gotcha. That makes a lot of sense now.
Yeah, I think the graphic is a huge help on that. I run into people all the time that, we kind of give them a vague, 50%, 70% is a good number, but the graphic helps a lot.
I mean, the truth is 20% is probably the good number. There's a question here about the comparison between machine time on the two. Nick, can you qualify? Was that about the adaptive clearing, or was that question in regards to some of the other toolpaths?
Well, I think while he's answering that, I'm going to chime in. I think part of the important equation here is, some machines, the column, moving up and down, the acceleration and deceleration is more time consuming on some machines than others, right?
Yeah, and it's not necessarily a one-to-one, even if you say your rapid's 1,200 inches a minute. If the move is only an inch long, it might never actually make it to 1,200 inches a minute. So we might think the simulation's going to be faster, but it never actually made it to full speed going up and then stopping, coming over, and going back down again. So
yeah,
there's a number of factors, and that's why we give you a sort of a massaging percent range to pick the factor where you say, this is the point at which I want to do a rapid instead of staying down.
Or that stay down move down there is, it's nice big arcs. So the machine, I'm not suggesting that you sway it to stay down more, but that's where it's important from machine to machine, because that's a nice kind of arc move that the machine might dance around pretty nice and reposition pretty nice down there.
And then you also have your no engagement feed rate too, which is worth noting.
Yes, it's a good point to talk about. That wasn't really part of the large data set conversation, but this one can actually be embarrassing sometimes if you really aggressively put up your cutting feed rate and inadvertently leave your no engagement feed rate to be slower. I may have done that in front of customers more than once. So this is the feed rate at which it's coming back. There's also a kind of a distance that it's going to step off. If you're kind of new to the product, there's a lift height that you can use so that it's not dragging across the surface. We call a micro lift. It's coming up just enough that it's not dragging, but it's not a full wrap it up. Yes, Rob, it needs to be tied to a machine configuration, something that we don't have in all products yet. I think today we have Jeff Tech and Renee on the line. So I'm going to say it, we're looking at prioritizing some effort on that next quarter. When there's stuff in customer hands, it would be a little farther out, but it is very high on our priority list to get machine configuration so you can refine these sorts of things on a machine-by-machine basis. There's a question from Gavin, and it's kind of funny. You said @Reckless Gavin. You're wondering if you can set the non-engagement feed rate to be a rapid movement. This is actually an interesting point. Many machines, Haas included, will do what we call a dogleg rapid. So if you have rapid motion, there's no examples on this part. Maybe in my kayak I have some, where the rapid is moving in X and Y at the same time. There's some long ones here that would probably catch you. So see these really long rapid movements that's going from this top corner to down in the bottom corner. You'd think that it's going to go the way the crow flies. Many machines accelerate all the axes until it gets to the right number. So if you're going over 30 inches in X and 2 inches in Y, X and Y are going to go at the same speed until Y has hit its value, and then it just goes across an X until it gets to its value. So you end up with a 45 in a straight line. So it's not going in the direction you asked it to go in. It's going to do that dog leg. We actually have an option in the Haas post that's on by default to force rapid movements into high feed rate moves so that we know where the tool is going to go. And especially when you're down in the pocket, you wouldn't want to use a rapid because then if it does dogleg, you're doglegging into the part. It's something that can happen if you turn that off and you're using our 3D operations. In the 3D operations, we have this shortest path linking, which finds those rapid movements through the part like that, and it can catch you by gouging into your part. So, Gavin, to answer your question, you want to be very careful with that, especially when you're in the part, because a rapid is saying get from here to there as fast as you can. A G1 move is saying get from here to there, and you have to follow the line between the two.
I'll just two more points. If the rapids would be doing dogleg, then we wouldn't be able to simulate it as it's actually running on the machine. So we really want to make sure that what you see in the simulation matches what you get on the machine. So it would be very dangerous to rely on rapid motion for these kind of moves, because there could be some deviation. And the second point is that a lot of controls will have different kind of smoothing behavior for rapid moves, and many controls would not really like you to have a lot of motion with G0s or rapid moves. They would cause a lot of stopping and restarting. So in a lot of cases, at least, just high feed G1 moves will actually run smoother on machines.
And for any of you that are hearing that voice, wondering who that is or where that's coming from, that was Renee talking. Renee leads the kernel team and the post-processor team. So now that you've spoken up, Renee, if there's anybody on the call that has deeper questions, now's a great time. It's good to have developers join us on these webinars.
I'll jump in and say that there are some machines that the high feed rate and the rapid rate are the same. So you would just put whatever that value in, and then the control handles the kind of the acceleration, deceleration better in that high feed move than a rapid.
the advantage is, and I'm going to say this as a warning for anybody listening, when we do force out the cutting feed rate move, it is the safer thing to do. It can scare you as an operator because if you've got your rapid set to 5%, obviously we're not setting that high feed rate move to 5%. Just again, an aside to keep in mind. Rob Lockwood wants Renee to very quickly cover API.
Rob, very quickly.
Rob, you're going to have to come to AU for that and vote on Renee's class. Renee did stick his hand up and say he'll do a post-processor API and touch a little bit on API too at AU if she can.
Nick, that's a very good question because I've actually seen quite a few times where putting most for your stay down distance will cause the toolpath to try and find really long ways around but stay down when in fact it could have just gone up and around the part and be a faster movement. Even if it wasn't a rapid movement, it'd be faster and shorter.
The truth is there's seldom cases where above 50% is going to be faster on the machine. My gut says most of the time it's going to be about 20%. I'm curious to hear what Rob said, some of you guys. I think Keith's an expert on today. Feel free to put in. But at 50%, you're saying that the stay down distance is exactly the same as the rapid distance. So from that, you know it's going to be something less, and then it's a factor of what's my feed rate difference and what's the decel impact on that.
I can chime in. I've tested it quite a bit, and I would say just using a Haas as an example, a little DM1 can move around a lot quicker than something like a VF8, right? So the column on a VF8 takes more time to move up and pause and move over and pause and move down and pause. Where that's where all I was saying earlier. I would say 20 to 70% is the window that I usually find, and 30 to 50% is where I usually find myself kind of leaving it.
So our first official level 70, Rob Lockwood, is saying he uses 30%. So hopefully that helps some of the rest of you have a good starting point. It's an interesting tool. If the boss walks by and says, why is the tool up in the air so much, you can walk him back and say, let me show you the toolpath calculation and prove to you why it's actually faster to do that.
And chiming in also, changing your clearance heights and your retract heights also helps a lot because like on my smaller machine on the Pocket NC, the default's pretty tall relative to the amount of space I have. So moving that down for me gives me a lot more speed overall.
So we kind of got off topic from some of the toolpath calculation side of things. I don't know, Renee, do you have any tips, tricks, comments you want to make in regards to the kernel and some of the surfacing toolpaths? Anything that I missed, things that you think people should know about how we calculate and what can make things calculate faster?
Not so much about the toolpaths calculation, but regarding the stock simulation, we have these two major modes, the 3D fast mode and the standard mode. And we don't really have one good stock simulation that can be used in all different cases. They each individual mode comes with their own limitations and advantages. So it's really up to you as a user to know when it makes sense to use one of the modes. And the 3D fast mode, of course, is only for 3D toolpaths, where the standard mode is for index multi-axis toolpaths. So you are limited in what you do, but you get sometimes nice functionalities by using the 3D mode, 3D fast mode. So if it's just 3D toolpaths, then that mode would capture a lot. It won't do collision checking, but that runs in Fusion in the background automatically, so you will still see if there's any collisions detected. But it's hard to make one good engine that kind of like covers all different use cases and is still very fast at the same time. So that's why it is as it is here in the user interface.
It's always a balance. We don't want to clutter the user interface with too many duplicate things, but there's definite times where there's the right tool for the job, and the trick is making sure that we get the right tools without just throwing everything in. So it's good to be able to work together with you as customers to help us drive that.
Renee. Renee, regarding the simulation, the stock simulation, why is it that going in reverse causes it to regenerate up to that point?
That's happening in the standard mode. In the 3D axis, 3D mode, it doesn't have to do a full recalculation. But of course, if you move it very far back, then it's sometimes faster to simulate forwards again. But the standard mode it can only calculate progressively. In particular, because it has to do the collision checking, it cannot reverse the stock simulation. So that's one of the benefits for the 3D mode, where the standard mode is require you to recalculate everything from the start. We will improve that such that we can cache some of the stock calculation, so it will be faster, but the principle, it still has to calculate from the start.
Almost like as if you had like checkpoints along the way.
Yes, exactly.
We got a nice, very direct question from Gavin. I'll answer it directly. You're wondering on how True 4-axis is coming along for Fusion. I'll be frank. What we've done with the wrapping of 2D strategies, it was the kind of the first step. What we had in HSM Works was a axis substitution for our 3-axis strategies. We're not looking at pulling that over, so it's not like in the next month or two you're going to see a whole bunch of new 4-axis strategies in Fusion. We are working on a blend strategy that will work to lay a toolpath around parts and could work very nicely for 4-axis, but don't expect something in the next 2 or 3 months. And stay tuned to the updates. I want to make sure we're transparent so that you can run your businesses accordingly, though. Matt, I guess we'll let you wrap it up. Thanks for the questions. It seems like out of this one, we've got a discussion around tool library. To do it next week would be immature, but we'll certainly do one in the very near future. There's a lot of development happening on it. I know we've talked about that for a while. There really is a lot of development happening here, and we should be able to communicate something out. It would be good to do it on a webinar like this. So.
Great. Well, thanks, Al. Thanks for the entire team that chimed in. I think that was a nice engaged discussion based on a topic that was really just surfaced this week. So, as usual, we encourage you to invite others, invite friends. You have direct access to the applications team, the development team, the product manager. This is a fantastic way to get direct feedback on what's going on in the product and answer your questions live. And for everyone in the Americas, have a nice long weekend, and we'll look forward to seeing you next Friday.